Anybody? All right, I see somebody sending something in the chat. Let me see here. Um, yeah, particles in constant motion, precisely. So the kinetic energy. Let me see what Erin is saying here. So molecules possesses energy and loses energy, of course, right? So as you can imagine, we're talking about kinetic theory, so it has to do with kinetic energy for the most part, right? So obviously, what we're going to do here is to look at it from a gas standpoint and see what is happening inside of a gas, as it relates to the molecules and how they are behaving in terms of when pressure is applied to it and so on, right? So that's essentially what we're going to look at. And we're going to look at the assumptions that are made as it pertains to the kinetic theory of gases, which we must be able to at least recall at least four of these assumptions, right? So this is the first assumption, right? One of the first assumptions is that gas is made up of small particles that are randomly moving at high speed. So that's an assumption that the kinetic theory has put forward to us, right? And we have further assumptions that we can make as it pertains to the kinetic theory of gases. Now, as you can see on the screen, it says that all the molecules that make up the gas are similar in the sense that they have the same mass. So that's an assumption that we're going to make in this case as we study the whole aspect of kinetic theory. Right. Now, the next thing is that the assumption that we're going to make here is that the collisions, right, are elastic, which means that the kinetic energy is conserved. So when we have elastic collision, right, if we can recall anything about elastic collision, let's look at it here. If I have a particle, right, that is moving with some initial velocity, u, and I have another particle that is stationary over here, when they collide with each other, right, this one here is going to come to a complete stop, and the one that was stationary is now going to attain the same velocity that the initial one had. That's what we mean by elastic collision. Cool? And we say that in an elastic collision, the kinetic energy is conserved. The whole reason why the kinetic energy is conserved is because the initial velocity of the first particle, right? When it collides, the final particle will have that same velocity. So that's how we can literally say that it's going to be conserved. Now, let's look at this now. It says that the intellectual molecular forces between the molecules of the gas are negligible. So we're literally saying that there's no potential energy associated, because what you have to understand is that when you have the particles together and they are close together and all of that, right? They will possess some amount of potential energy. But in this case, we're saying that there are no forces that are there. So if there's no forces, if there's no intellectual molecular forces, right, then it simply means that there's no potential energy. So that's an assumption that we're saying that it's negligible. Now, the next thing here is that the time of the collision is negligible, right, when compared to the time between the collisions. I don't know what they mean by that, but if you understand that point, you can elaborate on it. It says that the time of the collision is negligible. So I'm guessing they're saying that the time of the collision happens so quickly that you don't even record it. You can't even record it on a regular stopwatch mainly. You follow what I mean? It happens so quickly. Let me know if that's what it sounds like to you. Right? So these are some assumptions that we're making here as it pertains to the kinetic theory of gases. And as you could have seen earlier on, that the syllabus asks us to discuss the basic assumption of the kinetic theory of gases, right? It asks us to do that. So we ought to be able to pull on these assumptions if you're going into an exam. You see what I mean? So you have to remember these. So I hope you're taking down notes and all of that. It sounds like the time taken for a collision to occur is practically zero. Yeah, especially compared to the time between each collision. Yeah. So it's just saying, how quick the collisions are occurring. You know what I mean? That time, it is very small in a sense to measure on a regular device. So in a sense, they're just saying that those collisions are happening so fast that you can't even record the time, mainly. Right? So these are the assumptions, guys. And we have to can recall these assumptions. Any questions so far? So as we said, the broad assumption for the kinetic theory of gases is that the gases are made up of tiny particles that are constantly moving in random directions at high speeds. So that's a main assumption that is surrounding the kinetic theory of gases, right? Remember when we looked at temperature and all of that, we were able to use the whole kinetic theory to explain heating and how temperature operates, right? So, and when we were doing that, we had to look at it from a molecular standpoint. So it's the same thing that's occurring here, right? But it's just that we're not looking at temperature, but we're looking at how gases are behaving, so to speak. All right. So those are the two main areas that we can think about the kinetic theory coming into play when we're dealing with gases, with the particles in the gas, and also when we're looking at temperature, right? Because in essence, we know that heat is basically that total amount of kinetic energy that the substance possesses, and that kinetic energy has to do with how the particles are moving, right? So remember those kind of things and how we can use the whole aspects of kinetic theory to understand it. All right, I'm going to next slide now. Right, so now the beautiful thing is that we are now going to be able to can understand pressure, right, of gases to a certain degree by way of using the kinetic theory, right? So that's what we're going to do now. So when we hear that, pressure is inside of a container, so let's imagine that you have a car tire, right? And you pump air into it, and that car tire has been inflated. What is really happening inside of it, Obviously, pressure is being exerted inside of the car tire, but what is really causing that? It's obviously going to be as a result of, the particles constantly moving and colliding against each other. That will increase the pressure. But not only that, when you think about car engines, right, and how the engine work in terms of the gas coming into the cylinders, right, and having to be compressed, to become ignited and all of that kind of crazy stuff, right? We have to get an understanding of how, gases work and what happens if you were to, shrink the gas or to shrink the particles. You know what I mean? So if you are reducing the space, if you check this out, this is almost like what is happening in the car cylinder. So imagine that you have some gas inside of here, and you're now pushing down the piston on the gas. What you're doing, you're lessening the space that the particles have to move. And by doing that now, it makes it a little much harder for the particles to move. So they are going to vibrate much faster, thus resulting in them colliding more, and would essentially, what would I say now? Increase the pressure inside of the cylinder. And by increasing that pressure, you can now cause the gas to become explosive in a sense, right? Because if you apply too much pressure to something, it can explode, right? So we're going to look at that. So it says that suppose a container is filled, right, with a gas. It says that the gas exerts a pressure on the walls of the container. It says that this pressure can be measured using a manometer gauge. It says that the kinetic theory can be used to explain why, gas exerts pressure on the inner walls of the container. So we're going to look at that. So we said, that once you have gas in the chamber or whatever container it is, and if you were to apply some type of pushing force down on it, you're essentially going to cause the particles to have less space to move. You know what I mean? And with that, no, you're gonna essentially cause them to start vibrating more and all of that. And of course, if they're vibrating more, they're going to exert more pressure on the walls of the thing. But let's look at what it's saying here. It says that the molecules of the gas are moving around, um, colliding with the walls of the gas by. Let me say that again. I don't know. It seemed like I did not copy this properly. Seems to be repetitive. Uh, so the molecules of the gas are moving around. More than likely moving around in a manner colliding with the walls of the container. All right. It says that when the molecules collide with the wall of the, it seems as though something is not right here. Something is repetitive. It says when the molecules collide with the walls of the container, right? These undergo a change in momentum, right? So let me just kind of see if I can edit this quickly, right? There. All right. So molecules of the gas are um, moving around. But the essence of this, though, guys, is to say that the molecules are obviously constantly colliding with each other, and of course, not only colliding with each other, but they are also colliding with the walls of the the container, right? And when they do that, they undergo some type of change in momentum, right? So that is essentially what is taking place there. When the particles are inside a container, right? And on a whole, that's what is happening. So if you were to take up an aerosol or some type of spray right now, right, you might not hear the particles moving, but the particles are actually always constantly moving around inside of the container, right? And with that being said, they know they're basically exerting pressure because once they're colliding against the walls, right? That's how they're essentially pushing pressure on the walls of the container, right? There's some typographical error in this thing or something of that nature, so I have to go fix that eventually, right? But that's what it was saying there. So because of that constant collision that is taking place between the walls of and the particles, there's some type of change in momentum, and when that momentum changes, right, it essentially would um let me see here. So remember we said that the collision is elastic, right? So it's just a matter of just having a lot of collisions taking place, I was going to say that the particles would slow down to a lesser degree, but because we're saying that the collision is elastic in the assumption, then we can just say that they're just constantly moving up and down, and of course they will be exerting pressure on the walls. But let me know if you guys have any questions or you understand what we're saying here pertaining to that. Okay, all right. Now, whenever we're talking about gases, right, it's of paramount importance that we take into account the laws that govern gases, right? So there are three main laws that we know about for now, right? That you know explain to us what happens when we do certain things to a gas, right? The first law here that we can think about is Boyle's law. It's not the first time we're hearing about that, right? And what Boyle's law has to say to us is that when the temperature is constant, which means that the temperature is not changing, so it could be at maybe 50 degrees or 50 Kelvin for argument's sake, right? It says that the pressure, right, and volume are inversely proportional. So what this is telling us is that as the volume decreases, right, pressure is going to increase. So when we think about the cylinder or the car engine, right, the whole reason why that explosion occurs for the most part is because you are compressing the gas. When you're compressing the gas, you're reducing the volume. And if you're reducing the volume, you're lessening the space that the molecules have to move about within itself or within the body of the fluid or the gas for the most part. And that is now going to increase the pressure that is going to be exerted on the walls, right? So that's the first law that surrounds gases. We generally call these the three ideal gas laws. So that's the first one, right? That just signifies what happens if you were to keep the temperature constant in this scenario. Because the reason why we keep the temperature constant, guys, is because we know that if the temperature is changing, that can change the way how the molecules are going to react. And you don't want to change that. You don't want to interfere with how the molecules are reacting in this portion, right? So that is essentially what is taking place here. And for that reason, we can come up with this equation that says P times V is equal to K, where K is our constant of proportionality. Now, we can just modify the equation a little bit to say that P, right, is equal to, where P is the pressure, is equal to K divided by volume. So now we can see that, pressure and volume, they are inversely proportional to each other. And if you were to plot a graph of this, right, pressure would be on this axis, volume would be on this axis. You would have a graph going down like this. Which just goes to show that as you increase the volume, the pressure is decreasing, but as you decrease the volume rather, pressure is increasing. So let me say that again. So this is what the graph would look like. Obviously, it's an inversely proportional graph. Now, if I increase my volume, I am decreasing pressure, which is inversely proportional. If I decrease my volume, I'm increasing pressure. So that's how the graph looks. Let me know if you guys understand.
Yes, sir.
All right, good. All right. Now, next ideal gas law is Charles' law, and obviously most of these are named after the persons who kind of experimented these things. So the next one states here for Charles' law, we must remember, or we must know what is kept constant. For Charles' law, pressure is kept constant. And when we look at that, so when we keep the pressure constant, the only two things that we can vary in this case is going to be the volume and the temperature. So what we're seeing in this case is that when pressure is kept constant, we see where volume is directly proportional to what we call the absolute temperature, right? So if I'm increasing my temperature, or if I'm increasing my volume, right, chances are let's talk about the temperature instead, because what you have to understand is that volume is going to be the independent variable, whereas temperature is going to be the dependent variable, which is going to go on the y-axis. So so let me say that again. Let me see if I said that correctly. What are we going to? What is it going to change? So it's okay. So it's yes. So as temperature. So because we're essentially going to vary the temperature, right? The independent variable is one that you don't vary. You understand, right? So we're what is going to respond in this case? Let me just look at the graph for this one, because I don't want to say the wrong thing. Give me a second here. Charles' law. Right. So with Charles' law. So I think I said, all right. So temperature is going to be on the x-axis, right? Temperature is going to be on the x-axis because volume is what is going to respond. Volume is what is going to respond. So yeah, that's what I was supposed to say. All right. K is a constant. Is a constant. We soon talk about K differently though, but it's a constant. Constant of proportionality. Right. We soon kind of give it a name. When we go to the ideal gas equation, or the yeah, equation of a gas, an ideal gas. So here we are saying now that temperature would be your independent variable, right? And volume is going to be the dependent variable. So as I increase my temperature, I would expect that my volume is going to increase. So if I were to sketch a little graph here, right, it would look more like this. So temperature is on this side and volume is going to be on this side. And of course, we say it's directly proportional. So that is what is essentially happening. So if you apply more temperature to the gas, it's going to expand more and the volume is going to increase. All right, so that's how this graph looks. Let me know if you follow and understand what we're saying here. Mind you, whenever we're dealing with the ideal gas laws or gases on a whole in this area of the syllabus, the temperature is measured in Kelvin. So that's the reason why we use T for representing temperature and not degrees Celsius, right? So just be mindful of that. And if you're hearing something about absolute temperature, it's really coming from zero, all right? Starting from zero and going all the way up. Now, if you have any questions related to that, let me know though. Like, if you understand what we mean right here with the Charles law and all that. So we're keeping the pressure constant. Pressure is not changing, right? So with this now, we're seeing here that if we were to really transpose this equation, we're seeing that V, right, is equal to K times T, which just shows us that V is directly proportional to T, where we say that V is our dependent variable and temperature is our independent variable. All right. So we move on now to what we call the pressure law, right? Pressure law is when we keep our volume constant. So when we have our volume at a constant level, right, we can see where pressure, right, is going to be directly proportional to absolute temperature. So what that is just telling us is that as my temperature increases, right, I would expect the pressure to increase as well, providing that the volume is kept constant. So you would get a graph looking like this, right? So you can transpose equations and say that P is equal to K times T, K times T. So yeah, how we can keep the volume constant, guys, is by maintaining the size of the container. So if you don't change the size of the container, you don't expect the volume to change. So that's how you really keep the volume constant. Or you can start out with a set amount of volume, right? So that's how we keep it constant. Okay. So once we're through with that, we're gonna move on to looking at what we call the ideal gas equation. What the ideal gas equation is going to show us, it's going to show us a relationship between all of these three laws that we have discussed a while ago. So we have looked at Boyle's law, right, where it says that pressure is inversely proportional to volume. We have looked at Charles' law, where we say that volume is directly proportional to temperature. We have looked at pressure law, which says that pressure is directly proportional to absolute temperature. Now with the gas equation, the combined gas equation, or the ideal gas equation, this is going to basically ties in to all the three relationships that we have talked about, or all the three gases, the three laws that we have talked about just now. If we look at this, somebody remind me of what Boyle's law said a while ago. What is it that we kept constant for Boyle's law?
Temperature.
So we kept temperature constant. So in this case, if temperature is constant, mean that it's not going to change, right? What are we left with? So let's imagine that we kept this constant. So it's a constant value. We're left with P times V equal to the K constant, right? When we do transpose that, we would essentially get that P upon T is equal to K upon V, which just tells us that, pressure is inversely proportional to volume. Similarly, if we were to look at which other one now? What did Charles' law say? Charles' law is when pressure is kept constant, right? Is that so? So when pressure is kept constant, is it? All right. Give me a second. So let's go back over here. So we're looking at the first one, which is Boyle's law. In Boyle's law, we said that temperature is kept constant. So when we look, if I keep temperature constant, right, what we're left with is T times V equal to, K, the constant. So if we were to just manipulate the equation, we can simply see that T is going to be inversely proportional to V by way of just manipulating the equations, providing that temperature is constant, right? Now, Charles' law is one that says that pressure is going to be constant. When pressure is constant, I am left with volume, temperature, and my constant mainly. So that now is going to show me that volume is going to be directly proportional to temperature by way of me just manipulating the equation. So imagine that pressure is constant. Let's imagine that pressure is 5 for argument's sake, right? And that's a given number. It's constant. It's not changing. We're left with V over T equals to K. Now all we just need to do now is to just transpose to just show you that V is going to be directly proportional to T. So we have 0.5 V equals to T times K, which is just showing us that V is directly proportional to T, right? So with this equation that we're showing you, this equation here, it just explains everything, every law that we have looked at. The other law would have been the pressure law. With pressure law, we say that volume is kept constant. When volume is kept constant, right, we expect that pressure is going to be directly proportional to temperature. So if I keep this constant, so it's not changing, right? Then what I'm left with now is T divided by T equals to the constant, which is now going to show me that T is equal to K times T times V, basically. Because you have to put the V in the equation, because it's not like you can remove it. It's a constant value, right? So this is just this whole equation here is to just combine all of what we have looked at pertaining to the three laws, so to speak. Right? Any comments? Let me know if you guys are following. I mean, how you guys see? Okay. All right. So by just rearranging the equation, so sir, basically transposing based on the constants. Yes. Yeah. So what we're just looking at, so to just show us, to just prove to us that this equation here actually makes sense, is to just um you know look at what is kept constant and see what is left, and you will see that that is talking about Charles' law for argument's sake. Or if you look at, say, volume is constant, or then what is remaining, that it will apply to one of those laws, right? So that's really what is taking place there. So with this equation, we're just going to rearrange it a little bit, right? To say that T times V is equal to the constant of proportionality times the temperature. Now, it says that since the constant is dependent on the amount of gas used, which is measured in moles, it says therefore we have to write the above equation as such. So our constant now is really N NR for the most part, right? So this is our constant. I have less than a minute, right? So I'll soon restart the session. But what we're saying here is that in most cases, when you have proportional relationships or inversely proportional relationships, there's a constant of proportionality. Our constant of proportionality here is going to be NR. The whole reason why we're introducing N is because we're dealing with moles of a substance. You know what I mean? You understand? Because gases, you generally want to know the amount of moles that are inside of the gas and all of that. So that's how the whole PV equal to nRT comes into place, where NR is going to be that constant of proportionality. But you're going to see some modification to the equation when we restart here. So just allow me to restart, and then we'll rejoin, please, and thank you. All right. So this equation that you're seeing here is what we call the ideal ideal gas equation. Right, so that's what we call the ideal gas equation, right? We're going to use this to do many things. You might be wondering what we know what N is equal to. So we said that P is equal to pressure. We know that already, right? We know that V is equal to volume. By the way, use capital V for this, capital V for volume, right? N is going to be the number of moles, right? R, as you can see on the screen, is what we call the molar gas constant, molar gas constant, and that in itself has a value of 8.31 joules per mole per Kelvin, all right? And then of course we know that T is temperature in kelvins, right? Yeah, so yeah, man. So that's what we have there. All right. So let's move on now. So we must know this equation. We must know this equation. We must remember this equation, right? We must remember it. It's what we call the ideal gas equation. The reason why it's called the ideal gas equation is because it was derived from the ideal gas laws, right? So it pretty much just ties in all of what the ideal gas laws is telling us. Okay. Now there are certain things that we must know before we can move on further, right? And one of that is that we must know how to define a mole, right? We must know how to define what is a mole. So a mole is the amount of a substance that contain as many elementary entities as there are in 0.012 kilograms of carbon 12. So that's what a mole is equal to. Now, a mole of a substance is equal to 6.0 6.02 times 10 to the 23rd atoms or molecules. And if some of you do chemistry, you know that that is what we call the Avogadro's constant, right? So that is the amount of moles that are, or the amount of atoms rather, that is in 1 mole of a substance. So in every 1 mole of a substance, so if you have 1 mole of carbon, right, this is the amount of atoms that is going to be present inside of that 1 mole of a substance. And it's like it is a constant thing for every atom, so for not, well, every element I should say. So if you have helium, right, and 1 atom in helium, in a helium element or whatsoever it is, it's going to have this amount of molecules, right? Which is 6.02 times 10 to the 23rd, right? That's what we call the Avogadro's constant, right? And the symbol for that is Na, as you're seeing on the screen here, right? Na. If we wanted to find out the number of moles that are in some type of a substance, right? We must know the number of molecules that are present inside of the substance, right? And if we divide that by Avogadro's constant, then it can now tell us the number of moles that exist, right? So as we said now, in 1 mole of a substance, there is 6.02 times 10 to the 23rd molecules inside, right? When I say we must know how to define what a mole is, it's the amount of substance that contains as many elementary elements or entities, right, as there in um, 0.012 kilograms of carbon 12. So this equation is very vital. This one right here is very important for us to make note of. Because what you're going to see, we're going to do something to this equation very soon. This PV is equal to nRT. We're going to do something to it to get a more refined equation, right, so to speak. We're going to make some modification to that. I'm going to next slide now. So since we just found out a while ago that the number of moles is equal to the number of molecules divided by the Avogadro's constant, we can go ahead and substitute that into the ideal gas equation. When we do make that substitution, we now get this to say that PV is equal to the number of moles divided by the Avogadro's constant times the molar gas constant times the temperature in Kelvin. Now, we're going to introduce something what we call the Boltzmann constant. And the Boltzmann constant is nothing more than a regular constant. But how do we come by that constant? If I want to find the Boltzmann constant, I just simply divide the molar gas constant by the Avogadro's number. So, because I have that in the equation here to say that N over Na times R times T, I can just modify the equation to make it look like this, to say PV is equal to R upon Na, right? Na times Nt. So this thing here now, R upon Na is going to be replaced by what we call the Boltzmann constant, which is the symbol for that is a common K. So we're left with now that our ideal gas equation can now be written as PV is equal to N times KT. This is the value for Boltzmann constant. If you're doing any calculation, this constant is given to you. So you don't need to remember it. But if you remember how it is formed, then whatever the constant is not given to you, but you remember how we got the constant, then you can calculate it for yourself by dividing the molar gas constant by the Avogadro's number. So when we do that, this is the value that we're getting, right? Which says 1.38 times 10 to the minus 23rd joules per Kelvin. That's what the Boltzmann constant is. So our redefined equation now that we can use for the ideal gas equation is this. So, when it comes down to this aspect of the course, guys, we're going to come across a lot of equations, and you should know when to apply those equations based on what is given to you, right? So what if the question did not give you anything as it relates to the mole of the gas, right? And you need to find something, but you know the number of molecules, then all you would use is this equation, right? It doesn't change the price of rice, right? So that's just really what is going on here for this equation. Let me know if you have any questions. All right, no questions. All right, so make note of those two equations. Also, um, because we're talking about moles and all of that kind of thing, I think we should know how to calculate the moles of a substance, right? From chemistry days, some of us would know that to find the mole of a substance is to divide the mass of the substance by the relative atomic mass. The relative atomic mass here is that number that you see. Imagine that you're talking about carbon, right? Carbon, the relative atomic mass is this number right here. So that's the relative atomic mass. All right. So having said that, if I know the amount of carbon, that is present, right? Imagine that I say I have 16 grams of carbon, right? Then I can simply find out what the number of moles is going to be. And we generally work this in grams, guys, all right? We generally work this out in grams, right? So mass in grams divided by the molar mass will tell you the number of moles. So if you don't know the number of moles, but they give you the mass of the substance, of the element, and you know the mass, the atomic mass of the element, then you can find the number of moles. All right. Similarly, what if I want to find the molar mass of carbon? Right. I can also use this equation to say that the mass that is given to you of the substance, like that 16 grams. If I know that I have 16 grams of carbon, I can divide that by Avogadro's constant to essentially find out the molar mass of the substance. Okay? So these are two critical things, equations that we must also put in the back of our arsenal. Alright? Once you're through with that, just let me know. Alright? Let's just put what we have looked at so far in practice. So they want us to find the pressure of 16 grams of helium at 25 degrees Celsius, occupying a volume of 4 times 10 to the minus 4 meter cube. The relative atomic mass of helium is 4, right? Let's see if we can go ahead and essentially find out the pressure. So we know, of course, if we're going to find the pressure, right, we're obviously going to use this equation that says P times V is equal to, possibly, because we can find the number of moles, right, we could probably go ahead and say N times R times T, right? So P is equal to nRT, PV is equal to nRT, I should say, right? So having said this, this is the equation that we're obviously going to use to find the pressure, right? We're given the temperature in degrees, but we have to convert that into Celsius. My bad. We have to convert that into Kelvin, rather. We obviously need to find the number of moles that exist in 16 grams of helium. So we have to apply that moles equation. So at first, let's go ahead and convert to Kelvin. When we convert into Kelvin, we start off by saying T is equal to the temperature in degrees, which is 25, plus 273.15. When we add up this, we should be getting 298.15 Kelvin. So that's our temperature in Kelvin. As it relates to the number of moles, the number of moles, which the symbol for that is small n, is equal to the mass in grams divided by the relative atomic mass. So we do that. 16 grams divided by 4, right? We're getting the answer to be 4. So the number of moles now. Number of moles is 4. What this is telling us that we have 4 times 10 to the, well, my bad, 4 times 6 times, what I want to say is that if you have 4 moles in 16 grams of of helium, then you would essentially have, um, in terms of Avogadro's constant, you would have how much molecules now? So because we say that in one mole you would have 6.06 times 10 to the 23rd. Then in 4 moles you would have 4 times that number times Avogadro's constant to find out, you know. But you don't need to do that obviously. I'm just saying that for argument's sake. So having said that, we know that we have 4 moles of the gas now. We can then go ahead and find out the pressure using the ideal gas equation. So we can just further transpose the equation and say that P is equal to N times R times T divided by V. What was the R value again? The atomic mass, not atomic mass, the molar gas constant. What was that again?
8.314.
All right, 8.314. Thank you. And now we have the temperature, which is 298.15. Divide that by the volume, which is 4 times 10 to the minus 4, right? When we work out this now, somebody help me work this out and see what we're getting as the answer. All right, so Patricia, see your answer in the chat. Somebody just confirm that for me. See if that's what we're getting. Somebody just confirm. Come on, guys. I need somebody to confirm. Confirm. All right, let me just use my calculator. I see Jerome saying something there. All right. I think Rihanna and Patterson have the correct answer. Let me just verify again. No, not quite. I think there's some variation with it. All right. So yeah, yes. DeAndre. I think it's DeAndre. Yes, that's the correct answer. Rihanna, that's the correct answer. Patterson, work on your answer. I'm not sure what you did right there. Right. So the answer supposed to be 24 million 776,265 pascals, right? Or we could leave it as that, or we could even use the significant figures thing in a sense to kind of just make it a little bit better, or exponent. But yeah, right? So that's that as it pertains to that question now, right? So it's different because I put everything. Okay, yeah, yeah. So sometimes, if you put everything in the calculator, sometimes to be on the safe side, don't put everything in the calculator one time because some calculators are not that smart. You know what I mean? So 'cause maybe you have to put like brackets and all of that kind of crazy stuff. So just work out the numerator first, then you divide the denominator. You can't go wrong with that. You can never go wrong with that. So I'm encouraging you guys. You're gonna the exam, you work out some calculation. Please, not put everything in at one time. Better you work out the numerator part and just divide the denominator. You see what I say? Because we know that it can be a problem. Not all calculators are that smart. All right, so we're moving on now. Now, there's a crazy proof that we have to do. I don't know if we really have to do it mainly, but it's in the textbooks and all of that. I really don't want to prove it because it's a lot, but I think we have to prove it, right? What we're gearing at, it's a lot of things going on here, guys. A lot of stuff. Like, if we don't be careful, this can blow our minds. It's a lot of things that we have to prove here. You see, it's as much as how I'd want to just show you the equation and say, all right, work with this equation. Yeah, man, that's gonna go back. That's gonna go back. As much as how I'd want to just show you the equation and say, this equation is an equation that we can use to find pressure, right? And all of that. But it really wouldn't make much sense to you if you just look at it like that. You see what I'm saying? So, um, I think the better thing to do is to actually just derive it and done. Show you how you got it in a sense. It's gonna be a lot of things that you probably would have never imagined coming across. I've seen questions that actually ask us to derive the proof. You know what I mean? But sometimes you can probably say maybe they you not got they not got access to derive this one, right? So please, guys, when it comes down to deriving certain equations, don't take it lightly, right? I'm asking you that. Please don't take it lightly. All right. So, all right, Jerome, go ahead and screenshot this thing that you wanted now. So let's see if we can walk through this proof. I mean, it's crazy. So we want to derive, you see, a formula for finding pressure, right? While we have the equation that one a while ago, the ideal gas equation, we can essentially derive other equations to finding pressure. And of course, this is going to be somewhat related to what we know about pressure already. We know that pressure is equal to force divided by area. So we're going to kind of use that concept to derive an equation that we can apply specifically to molecules, to particles, or to pressure that is being exerted on a gas, right? So it says here, one of the first things that we're going to do, right, we're going to consider a cube, right? And in considering the cube, you know that the cube has the same sides, right? So we're going to consider that each side has a length of L, right? Now it says that one of these molecules, so we're going to single out one. Who's that? Okay. We're going to single out one molecule of gas to do this proof, right? So it says that one of these molecules has a mass of M and it is traveling towards the right wall of the container with an initial velocity u. So we're singling out one molecule of a gas, which is so bizarre, meaning that we can't really do that in a sense, right? Because there's so many molecules, it's so hard to do it. But in order for us to prove this equation, we're going to single out one particle. If we remembered anything about the kinetic theory, the assumption, we said that all the molecules have the same mass. So we just if we can single out one molecule or one molecule of the gas, then it can speak to every other particle that is inside of the gas because they have the same mass, they would be traveling at the same velocity, that kind of madness. And of course, we say that the collision that is going to take place is going to be elastic. So let's look at this now. It says that recall that from the kinetic gas theory, it says that the collisions are elastic. So for that reason, when the molecule collides with one of the walls of the cube, you would expect that the particle is going to return having the same velocity, or in essence the same momentum, right? So going towards the right, you would have this momentum. You would have m times v, right? And when you collide, the momentum is going to return, obviously. And whenever we're talking about velocity on a whole, right? We have to factor in the direction where the vector is going. So because going to the right was positive, now that the particle has now collided, right? It has now collided. It needs to go back in the opposite direction. So in this case now, the momentum that it has is going to be minus mu. The reason why u did not change is because the velocity is constant. Well, not a constant, but it is maintained in an elastic collision. So first we said that the particle goes towards the plate or goes towards the side with mu. When it collides, it's going to have minus mu, which is the same thing in a sense. Now, what if we wanted to find the change in momentum? If we were to find the change in momentum, you would see that change in momentum, right? So change in momentum is going to obviously be in this case they're going to have they're basically subtracting the initial from the final, right? That's what they're doing there. So when we check this out, we would end up having a change of momentum of 2mu. The whole reason why we get that is because this minus and minus is going to become plus. So if you have a plus sign here, so you have mu plus mu. So our overall change in momentum is going to be equal to 2mu. All right. So that's the first thing we're starting out with. That our change in momentum. So our delta p, we can write it as delta p. So the symbol for momentum is p as well. Delta p is equal to 2mu. Having said that, now let's look back. Let's look at what the next slide has to offer to us. Now, it says that before this molecule can collide with the wall, it must travel a distance of 2L, right? Therefore, the time between the collision is going to be equal to that. So let's look back at this. So it says before this molecule can collide with the wall, it travels a distance of 2L. So I'm believing that the collision, so let's imagine that the particle starts at this wall, right? It starts from this wall and it travels all the way over here. So that is going to be the first distance, which is L. Then after colliding, right, it's going to come back over here, right? And that total distance is going to be equal to 2L. That would have been the total distance. But obviously, because the particle is traveling back and forth, there is a time associated with that, right? And in order for us to find that overall time, we're going to use the whole equation pertaining to velocity. We know velocity, of course, is equal to, that in essence, the total displacement or the total distance traveled divided by the time. we want time to become the subject because we want to find that time in itself. So if we transpose, we're seeing that t is equal to 2L divided by u. All right. Yeah. So we must know that, right? Now the next thing that we're going to look at here is it says that using these two bits of information that we just looked at a while ago. So the whole momentum thing a while ago. So that's the first bit of information that we have. So we said that our change in momentum, right, was equal to 2mu. And just a while ago we found out that t is equal to 2l divided by u. If we were to put these information together to essentially find out the force, now if we can recall something spectacular from what Newton said about force, right? Force is equal to the rate of change of momentum, right? So because force is equal to the rate of change of momentum, we know the change of momentum a while ago when we looked at the molecule. We know the time, so we can now come up with an equation for force. So force that is exerted on the walls by the particle is going to equal to 2mu, right, divided by 2l divided by u. But we can kind of modify this a little bit. Because whenever we have this type of mathematics right here, we can sort of re-simplify it or simplify it to some degree. So this is what I'm going to do. I like to do it this way. So I'm going to take numerator and put it one at that position. I'm going to basically just break it apart to say that 2mu divided by 2l upon u. Whenever we're dividing fractions like this, we find the reciprocal. So we're now saying that 2mu times u divided by 2l. Clearly, this 2 is going to cancel this 2. So at the end of the day, when we check the stats, the force actually is going to be mu squared divided by L. So that's the force. All right. That's the force that is being exerted on the wall in itself. All right. Cool. I'm going to next slide. Can I next slide? All right. Now we're not there, but we're almost getting close to something. So a while ago we found out the force, right? Now by using our pressure general equation that says pressure is equal to force divided by area, as you can imagine, because it's that we're dealing with a cube, we know that the area of the cube is going to be length times length, which is going to be length squared. When we do that, right, this is what we're going to see here. So pressure is equal to force, right, divided by area. We found out that the force a while ago was mu squared divided by L, right? And now we're dividing that by L squared, right? Which is essentially saying u squared, right? Divided by L times 1 upon L squared. So when you do the math now, we're seeing that m times u squared divided by L cube is now our equation for for pressure, but we're not finished because we know that anytime we're cubing something, whenever we're cubing something, that becomes the volume, right? That becomes the volume. So we can now rewrite this to say that pressure is equal to mass times the velocity squared, initial velocity squared, divided by V, which is now my volume, right? So that's where we're at for now. But we haven't reached nowhere yet because we're gonna have to consider what is happening to the velocity in order for us to come up with some other stuff. All right. Let me know if I can next the slide. I know this proof can be a very daunting proof, right? It can be. Um, but I don't know of any easier way to go through it, right? Um, but let me know when I can next the slide though. Is it that you guys are still writing? Where did I lose you guys? Or maybe I lost you guys somewhere. Let me know if I lost you anywhere pertaining to this. All right. So we're at this point. Let me see something here. All right. So we're at a point now, guys, when we're going to essentially um, prove that pressure is equal to this. All right. So guys, I know we don't have much time remaining, right? But we want to get to this equation, right? That says pressure is equal to 1/3, right, times the number of molecules times the mass of the gas times the mean root, well, the mean square, the mean speed square, I should say. Am I saying it correctly? Yes, the mean speed square divided by the volume. So we kind of want to reach to this level, right? But before we can reach to this level in terms of the equation, because this is just showing you where we want to go, right? This is the equation that we're essentially trying to derive. In order for us to reach to that point, we have to understand that what we looked at a while ago was the pressure for one particle. We found out that information to be, if we have one particle, right, the pressure was equivalent to m times u squared divided by v. That was for one particle. But when it comes on to the number of gas particles in the cube, there are several particles, which means that you could essentially add up all of the pressure that these particles would exert on the cube or on the walls of the cube. So in essence, um, this is what you will be doing here. So firstly, what you have to understand is that the mass of the particles of the particles is going to remain constant. The volume is going to remain constant. The main thing that you're really changing is the velocity of the particles as they are moving back and forth inside of the gas. So what we could do, we could add up all of these in a sense. So let me show you what I mean. So uh, let's imagine that we want to find the total pressure of three particles for the most part. Now each of these particles have the same mass. So if they have the same mass, let's imagine that m times the speed square of particle 1. Now, as I said, the volume is going to remain constant, plus m times the speed square of the second particle divided by the volume, plus another one. So m times, u third square, right, divided by v. Then we could just we could simplify this because we're now saying that the mass is going to be constant, the volume is going to be constant, right? Because if you're containing the particles in a container, then the volume is going to remain constant because you're not losing volume, you're not gaining volume. The mass is always going to remain constant, so we can factor that out to say that m, right, times u squared for the first particle plus u squared of the second particle plus u third of the third particle, right? All of this, close that bracket, divide by the volume, right? We can clearly see that the total pressure would be equal to this, right? And this continues, guys. We're just using this to show three particles, but there are obviously going to be more particles, right? But we're just kind of showing what is taking place here. So having said that, we can just simplify this as such. Now we still haven't reached anywhere as yet, right? Because now what we're going to consider, right, is the fact that because the particles are obviously moving, right? They're going to have individual velocities and all of that. So we could find what we call the mean square speed of the particles. And how we find the mean square speed of the particles is by adding up all the speeds and dividing by the number of molecules that are inside of the gas. So that's how we find the mean speed, the mean square speed, right? And this is how you write the mean square speed with these brackets here. That's how we do it, right? Mind you, that C in this case is talking about the speed and not the speed of light. So you have to be careful about that. It is the speed of the particles, right? So our mean speed, our mean square speed rather, is equal to the individual speed of the particles squared, divide that by the number of molecules. So if I go back to this equation, right, I can now do a little bit of modification here, right? Because I don't want all of these speeds here. I want the mean speed. So what I'll be doing is to pretty much substituting, I'm making a substitution for the most part into the equation for C squared, right? So when I do make that substitution, but before I do that, it's best if I make u1 squared plus u2 squared plus un squared becomes the subject, and in order to do that, I must transpose here, right? So when I transpose, I am now getting that my mean square speed times n is equal to all of this thing right here. So what I'll do, I'll go back to this equation and I'm going to substitute for this. So when I substitute for this, I get that P is now equal to M, right, divided by V, right, times N times C squared. Well, yeah, the root, the mean squared, the mean speed square. I hate to call that word. The mean square speed, right? So this is now, we're almost there, because if you look at the equation, we have most of what we need. We have N, we have M, we have the mean square speed, we have the volume. But we're now going to go to this part in the next, well, we don't have enough time to reach that point. But I just want you to understand. But let me just say something here. That this speed that we're considering, right, is just the speed for what we call the x-axis. Now, further on in physics, you're gonna find out that there are three axes. You have the x-axis. I don't know if I drew this correctly a while ago. You have the x-axis, you have the y-axis, and you have the z-axis, right? What we just considered a while ago was the mean square speed for the x-axis only. Because the particles are obviously moving in random directions, we would have to factor in all the axes that exist, which is going to be the z-axis and the y-axis plus the x-axis. So that would take us into this kind of crazy thing going on here, right? That's how we would have gotten the 1 upon 3 in the equation, which I will explain that in the next lesson, right? Because it don't make sense to rush through the process. But I'll send you the information so you can read through it and see for yourself, right? But what you come to understand is that the pressure that is going to be exerted on the x-plane or the x-axis is going to be the same pressure that will be exerted on the y-axis, and it's going to be the same pressure that will be exerted on the x-axis, right? So similarly, we're saying that the mean square speed on the x-axis is obviously going to be equal to the mean square speed on the y-axis, and also equal to the mean square speed on the z-axis. Now, what we're trying to find here, so what this right here that you're looking at, right, is this right here now would be, if we were to add up all of these individual average if we were supposed to add up all of these mean squared speed, right, you can get a much redefined value for your mean square speed, which is this thing right here, right? This is what we want in a sense, right? And not this, because we already know that cx squared is obviously equal to cy squared. We know that already. So all of these things right here are going to be basically equal to the same thing. So in essence, we can just add them together to get three 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 what do you call it now? The mean squared speed, right, of the x-axis, because they're all the same values. They're all the same values, and with that, it's going to take us into some substitution here. So I'll definitely go back over this part, right? I mean, it's a lot of stuff that really can be confusing sometimes, but I'll definitely go back over this part, right? And I'll send you the information so you can go through it and see it for yourself, right? I mean, there's no easier way of looking at it, right? So I'll definitely do that.